find out, I'm taking a piece of it to David Muller at Cornell University. He's offered to show me how the atoms in our bronze stack up. Literally.
Oh, I see. I brought you a couple of hunks of bronze, one of which was knocked off of the bell when it was done, and one of which is unpoured. And I wouldn't mind taking a look at these under your magic microscope.
Okay, now, this is actually a lot of material. I need an area about the size of a farm, and you've given me the whole of the United States. So we're going to cut it down a little bit. Now, watch out, it's hot.
It's what? Ow!
First, a polishing wheel gives the bronze a mirror-like finish. Then the sample is inserted into a powerful electron microscope. David tells me that when we reach full magnification, we will have images of the actual atoms in the bronze. Something few people have ever seen. Frankly, it seems a little far-fetched.
So what's in there right now? What are we looking at?
So we have a piece of the bronze that we cut earlier, very similar to this one.
Now, I have to say, this microscope is not especially impressive. I mean, I'm seeing the entire circle like I'm just wearing a pair of reading glasses or something.
So this is like having a map of the United States, and eventually we want to zoom in, and we want to pick out one car parked somewhere in the U.S.
We'll have to zoom in 100 million times to see an atom. To understand the scale, imagine if I were floating in space 2,000 miles above the Earth, looking down at the United States. Zooming in 100 million times would allow me to pick out not just a car, but a bug crawling in the grass next to it.
So we can zoom in from here?
Absolutely.
How do you do that?
So there's the zoom button.
The big knob labeled magnification?
Absolutely. So crank up the mag and let's see what happens as you zoom in.
Wait, I see a little tiny cartoon sign that says, "Welcome to Whoville."
To see atoms, we need to find an interesting region to sample.
Now it's starting to look like an alien surface.
Right. Now what we're actually starting to see is the microstructure of the grains in that bronze. And the brighter colors are things that contain more tin. And the things with less tin are the things that are slightly darker.
Oh my gosh, that is so cool.
The microscopic structure of metals is not uniform. Small features called grains become visible. Boundaries between grains are actually defects in the orderly arrangement of the atoms.
So you can't see atoms with this microscope?
We can get almost all the way there, but not quite.
Okay.
And to look at atoms, we're going to need a bigger machine.
Do you have one?
We certainly do.
This huge thing? This giant room-sized thing in a shipping container? And why is it draped in shipping crate material?
Those are acoustic blankets. They are meant to absorb and reflect sound because the microscope itself is so sensitive that if you were to talk, just the pressure wave from your voice is going to give enough mechanical vibration to shake this thing around. We only have to shake things by an atom for the image to vanish.
Oh, so our little piece of bronze that we've dug out of the first machine is now the little black disc there?
Well, that's the 3mm support disc. The actual bronze chip itself is about 1/100th the thickness of a human hair. It's too small for us to see, so we have to mount it on a carrier grid so we can handle it.
Oh, so you've essentially put it on a little plate?
That's right.
Are you telling me that I can see individual atoms of my piece of bell?
That's correct.
Scientists have understood since the early 20th century that metals are crystals. That is, they have an orderly arrangement of atoms. By bombarding samples with X-rays, they were able to create shadowy images of that crystal structure. But the idea that we might one day see actual atoms was beyond imagination. If David's microscope is powerful enough, we should see regular rows of copper atoms with tin atoms packed in between. Or so the theory predicts.
The dots are atoms?
That's right. Each individual dot is an atom.
We are seeing actual atoms of my little bell piece?
The bright ones, those are the tin atoms, and the slightly darker ones, those are the copper atoms.
And isn't it kind of like a mind blower that we're actually looking at actual atoms? I mean, isn't this a historic technological achievement?
Every time people see that for the first time, they get really excited.
To actually see atoms. Amazing.
Well, what can we learn about this? Like for one thing, I noticed they're really, really grid-like. They're like a little aerial photo of a planned community.
That's actually the stacking of the atoms in the material. The pattern that it orders into, that is the crystal structure directly.
David tells me we got very lucky. The atoms in our bronze are unusually well ordered. Our bell makers must be true masters of their craft.
Well, thanks for my tour into the unseen, into what used to be the purely theoretical. I can't believe I can now put on my resume that I've seen atoms. Thanks for the tour.
It was a pleasure.
This amazing ability to see atoms has opened up new worlds for scientists. Muller's lab has successfully captured many other images of atoms in gold and computer chips, oxygen, powerful magnets, and even glass. But even so, they've barely scratched the surface, because they can discern only the outermost boundaries around atoms. The interior is 10,000 times smaller.